Anyway, dang it. Quickly to run through that again, since I forgot to start the video, we're going to be looking at probability and odds in a couple of seconds, and we're going to be using these definitions right here. And then with success, we're going to be writing, with probability, we're going to be writing those as fractions. We're going to write them as success to failure with a colon. And you'll see that in a couple seconds. Okay, so let's take, oh, and one other thing. Do you know how, like if I were to ask you a question like, hey, what's the probability that it snows today? And let's just say it was 20% or 0.2. And then I say, okay, if the probability that it snows is 20%, what's the probability that it doesn't snow? And you would say 0.8 or 80%, right? You just said you are built in, you have been built in or wired somehow, I don't know where you were taught that, but to understand what it means for a complement. Okay? So a complement is the probability of doing something is 1 minus the probability of not doing something. You just did that unknowingly. You said the probability of it not snowing is 1 minus the probability that it snows. And that sometimes is a really great way of getting a problem done. Dude, man, this is going to be so complex, me trying to figure out what actually could happen. But it's really easy to go 1 minus the probability that it doesn't happen. Like, for instance, do you remember that problem we did with the semicircle? And you had all these dots right here, and I was saying stuff like, how many different ways can you connect 3 dots and make a triangle? Remember this? And you had to find the number of ways you here, or 2 dots from here and 1 from here, or 1 dot from here and 2 from here. And then you had to add up all those things, right? Well, wouldn't it have been easier just to count up the total number of ways? And then subtract what couldn't happen? What's the only thing that can't happen? All 3 from there. So sometimes it's easier to count up the total of ways to do something and subtract what doesn't work. That's kind of the idea with a complement. Probability of guaranteed success is 100%. If something is guaranteed to happen, 100% or 1, because 100% means divide by 100, right? So if I subtract what doesn't work, I get what does work. Or if I subtract what does work, I get what doesn't work. So remember that complement. On your test, I normally set you up on a problem to use the complement. And I have, what it means is, what I mean by setup is, if you don't use the complement, all these individual probabilities, the probability that this could happen or this can happen, and there's like 10 different ways to do that probability. And you can do it that way, it just takes a lot of writing. But if you would notice that, wait a minute, that's the same thing as 1 minus what can't work, and you can knock it out in one quick step, that's something that you'll see occasionally. Hopefully, it'll kind of pop into your head that that's a good idea. But we're going to talk about complement as well throughout a week or so. All right, so we're going to start you off basic. I'm giving you probability that something occurs. Okay? So if the probability, is everybody with me on this page? Probability part 1. Yeah, this is in your actual book. This is not the supplement I gave you. I don't think it's in the supplement, unless I double printed it. So it says state the odds of something occurring given the probability that it occurs. So I'm asking you both about occurring. So if this is the probability of success right here, what does the 3 stand for? The number of ways for it to be successful. So you could call 3 S. And then what does the 4 stand for? Success and failure. So if the 4 is success and failure, just by the process of deduction, what do you know about F? F would have to be 1. Basic substitution principle. And now that if I know success and failure, what is the this is the odds. Dang it. No, that's right. So state the odds. So now what would the odds of success be if that is S and that is F? 3 to 1. And you would write 3:1. And if you see anything on my notes that writes it as 3/1 like a fraction, I think I've gone back and changed all those. I'm trying to stick to better odds format. The book that I used way back in the day had it written as fractions, and it's just not not commonly done that way. All right, same thing with this 320, I'll let you do that. What about this? State the probability of it occurs given that these are the odds. All right, and again, we're talking about them both occurring. All right, so if these are the odds that it occurs right here, if that's odds, say, of success, okay, if these are the odds, then what does the 6 stand for? Success, and what does the 5 stand for? F. Okay, so what would the probability of success be given those odds? Y'all see that that's 6/11ths? So 6 over the 6 plus 5. And again, we write probability as a fraction. All right, and then number 5, I'm kind of switching up a little bit on the rest of these. Number 5, it says the odds are 6-1 against an event occurring. So I'm saying what? The odds of, what do you want to call that? Against it occurring. Failure, losing. So I'm just going to call it, we'll put lose. The odds of losing. So that would be 6-1, which means 6 is your, like your failure, and 1 is your success. I'm even going to change that L to F just to be consistent. It's the probability that it will occur. So that's the probability of success, and what would that be? 1, which is success, over both. So 1/7. Y'all with me? We'll do this in 2. It says the probability is 3 to 4, or 3/4, sorry, that it will occur. So the probability of success is 3/4, which makes 3 what? And if 4 is S plus F, what do you know about F? F would be 1 again. So what are the odds that it will not? What are the odds of failure? Odds of failure. 1 to what? 3. Because remember, odds is just failure over success or success over failure. So 1 to 3. So this shouldn't be a huge deal. This is the kind of problem you probably see in your test. Something like this, just making sure you know that definition and how to go from one to the other. By the way, all the rules you're about to learn in probability are probability. So if I on a test, I'll think of an analogy in a second. If I on a test ask you a question about odds, you're not going to have rules for odds. What I mean by that is, like your fundamental counting principles, all the things that you're going to use to do these problems, the combinations, the permutations, all of that is based on probability thinking. So if I ask you a question about odds, what you need to do is think in terms of probability, unless it's really basic. Think in terms of probability, get your probability, then convert it. And you can see, you knew how to convert it right here. So do that for yourself. Okay, if you try to do these problems as they get more complex with odds, well, you're kind of like, you know how we didn't do anything with base 10 or not base 10, base 8 or base 16, but do y'all remember doing base numbers with like Kyrie or whatever? And they ask you a question about base 7. Like, for instance, have you ever added in base 7? You know the problem with adding in base 7? Your brain doesn't know how to do that. If I was 5, you tell me what? You tell me 8 in base 10, but if you tell me 11, what did you do to get, that is the answer of 3 plus 5 when it's in base 7, but it's not 11 like we know it. When we know 11, we're thinking there's 110 and there's an additional 1. But when you're dealing with 11 in base 7, there's 1/7 with an additional 1. That's the 8 we get. But for her to get that, my guess is she thought about it in base 10 and then quickly converted it in there. Like in my head, I'm thinking, okay, there's 8, so there's 1 set, but I said 8. My brain thinks that way. Same thing with probability and odds. Think in probability, convert it to odds if you have to. Because if you try thinking in odds, your rules aren't going to work that well. Now, with where everybody had 8 fingers and 8 toes, you probably would have a base 8 number system, because that's why we have a base 10 number system. And if you did, you probably would have learned to count that way, and 3 plus 5, of course, is 11. It's one set of hands with an extra digit, right? That's how, or one set of fingers with an extra digit. That's how we would have learned, but we didn't. Say things that are true, but I'm going to try to stretch your brain a little bit and use combinations and use permutations in addition to what I'm showing you to help you think a little bit as it gets more complex. And also remember, there's 2 things we talked about dependent and independent. And give me an example of like a dependent situation when it comes to counting a probability. Dependent. You can do it.
Drawing cards.
Drawing cards. You pick a card. What happens on the next pick? Changes. It's affected by that first one because there's less cards. There's less of whatever kind of card you pick, less of whatever suit that you picked. Everything is changing. When that happens, you are allowed to use factorials, combinations, permutations. Independent situations. Give me one. Rolling a die, flipping a coin. And there are also some situations you're going to find that even though they technically are dependent, because of a lack of information, they're actually, we're going to treat them like independent situations. And I'll talk about those in a second. But if it's independent, you cannot use at all combinations, permutations. You can't, okay? And what I'm talking about is dependent situations that act independent would be like, what if I said Sam was a 400 hitter in baseball, career 400 hitter. Now, what are you thinking each and every time he gets up? He's a 400 hitter. Y'all know, a lot of y'all play baseball. He's got a what and what? 4 in 10 chance of getting a hit or whatever qualifies as a hit. All right, so 4 in 10 chance. Now, the second he gets up and hits, whether he gets on or whether he doesn't, what's happened to his batting average? It's changed. Go up a little bit if he gets a hit. It's going to go down a little bit if he doesn't. But the point is, if he had had thousands of at-bats over the course of his career, that one bat is going to change his average so little, I'm probably still going to think the next time he gets up, he's got a 4 in 10 chance. And even if I didn't want to think that, I want to be exact. If you don't have the information, if you don't know how many times he's hit, obviously if he's only hit 10 times and he gets a hit, now his average just jumps significantly. If he got 100 times up, 41 out of 101 is a whole lot different than 5 out of 11. So a lot of times if I don't know the information, I will just stick and say, oh, he's a 400 hitter every time. And kind of like when I flip a coin, there's a 50% chance or 1 in 2 probability every time. So sometimes I'll even take some of these situations that really actually in real life are dependent. And because of a lack of information, I'll go, all right, I'm just going to. If I say that the chance of rain this week is 40%, or what if I said the chance of rain today is 40%, and I look up on the weather app and it's 40%, like it's at 10, 11, 12, whatever. What if it just dumps at 10? And you've seen clouds that come over really dark and they just dump and all of a sudden it's light out. It's a lot lighter. Why is that? There's no more rain up there, right? It takes a while for that to evaporate. So happens, the probability of a future event is changing by that. But again, I might just say 40% for the day or 40% each hour because of the lack of information. All right. So anyway, let's talk about some of these. And I'd love some feedback if you want to give it on these. But I want to talk about multiple ways to write your answers. And again, as they get more difficult, you'll appreciate this. A card is drawn from a standard deck of cards. And again, does anybody have a question about how cards are made? I don't mean like the actual process by which they print the cards, whatever. But everybody knows that there are 4 different suits: clubs, diamonds, hearts, spades, right? And the cards go 2, 3, 4, 5, 6, 7, 8, 9, 10, and then jack, queen, king, and then an ace. All right. So if you know that, I say, what is the probability of each of these happening? And by the way, we don't ever need to simplify anything. You don't have to simplify There's 13 out of 52 hearts. You can leave it as 13 out of 50. You can if you want, but if you simplify incorrectly, it'll cost you. So what's the probability of getting a heart? Okay, so one way to do that is to say 13 over 52. Another way to do that is there are 13 hearts. I am choosing one, and the order in which I choose it does not have an effect on the outcome. That's the number of ways tends to be 13, right? And then I could say 52 C1 because there are 52 cards to choose from, and if I pick one, granted, there's no guarantee that it'll be a heart, but that's okay because I want successes and failures in the denominator. And this is going to be a whole lot better way to do it on the right when I ask you a question like, find the probability that I get 2 hearts when I draw 2 cards. And 2 hearts, I'm going to say 13 over 52 C2. Or if I said, find the probability if you draw 3 cards that I get 2 hearts and 1 spade, that's when it really starts becoming helpful. Because just writing them out independently like this, we're going to use this a lot when we have independent situations, can actually get you in a little bit of trouble, which we'll talk about. An ace. 4 aces, so 4 out of 52. So you totally can do that in this case. Kind of get your brain wired a little bit better. It's better to say in the future, 4 out of 52. It's better to say in the future, there's 4 aces, I'm going to choose one. 52, I'm going to choose one. As we become and get more complex, that's going to be a better answer for you. The ace of hearts. There's 1 ace of hearts. So 1 out of 52. Or again, there's 1 over 52 C1. And again, honestly, I wouldn't write this combination on a problem like this. I would have just written 13 out of 52 or 4 out of 52. But I want you to see that as we start becoming a little bit more difficult. What about number 10? It says 4 coins are tossed. Find the probability that 4 heads will come up. Now, is that a dependent or an independent? That's independent because that first coin being tossed is not going to affect the outcome of the second one. So I'm going to treat all of these independent of each other, and I'm going to look at them. So the first coin, what's the probability that you would have gotten heads? 1 out of 2, right? So 1 out of 2, and the probability on your second coin, again 1 out of 2, nothing's changing, right? And the third coin, so you can see in a situation like this, the probability that heads would come up is just 1/16, or you can write it 1/2 to the 4 times like that. If the odds are, I tell you what, I'm going to leave that for you. You've already talked about this. Also, sometimes when we're talking about rolling die, the problem can get a little more complex. If I were to say something like, all right, if you're rolling 2 die, I find the probability of you getting at least a 9, a sum of 9. Writing all those out and counting those up is one way to do it, but sometimes it becomes, when I say things like that, so sometimes a chart like this might be helpful. Writing all of them out and saying, okay, what's a sum of 9? Be like 6, at least a sum of 9 would be like 6, 3, 5, 4, 4, 5, 3, 6, all of those. And it might give you a visual where you can count them up a little bit more quickly, all right, rather than just trying to write them all out. That's going to be up to you whether you want to do that or not. But hopefully you see that if I'm rolling 2 die, there are going to be 36 combinations, right? 6 times 6 numbers of ways to do them. And you could just count these and say, all right, 4, 7, there's 10 out of that 36. And find the probability that way. And then if it did happen to ask for odds, I could simplify this and then convert it to odds. But it's probably sometimes probability. And I hate writing this thing out. So a lot of times what I do, if I'm having trouble with these, is I'll write like 1 through 6 and 1 through 6 and just put a bunch of dots. And that way I can kind of look at it and go, all right, 6 and 3 would work, 5 and 4, 3, 4 and 5, whatever. And I could count them up this way without having to labor over writing this whole chart up. So again, if it helps you, great. If there were 3 dice chosen, it becomes a little trickier because now there are 216 ways. And visualize 6 times 6. It's 6 times 6 times 6. It's kind of a 3-dimensional Thought you might have a little bit more trouble with those, but I don't get into that a ton. And we're going to talk about other ways you can count these as well. All right. Find the odds of getting a sum of 7. So the odds of getting a sum of 7 on a throw would be what? And again, if you had this chart, you could go, oh, sum of 7. You can get that, what, 6 ways. So there's 6 ways to be successful. Sum of 7, right? So the odds of getting a sum of 7 would be there's 6 ways to be successful. And how many ways to fail? Right? Because the total is 36. So subtract those 6 from it. And 30. Except we're not going to write it as a fraction. We're going to write it as 6 to 30. Or you could even write it as 1 to 5. All right? Jump down. Number 13. It says find the probability. If you have a box that has 4 black socks, 5 white socks, and 2 red socks, you're picking 1 sock. So if I pick 1 sock out of there, what's the probability that it will not be red? So probability of not red. I'm picking 1. So how many ways can I be successful there? How many? Not be red, so you could say 9 that it's not red. And how many total ways can I draw this sock? 11. So 9 11's great. I also, again, want you to think in terms of, well, there's 9 ways to do this. I'm picking 1. The order does not affect the outcome, it doesn't sound like, whether I was picking 1 sock or 2 socks or 3 socks. And then there's 11 C1. And thinking in terms of combinations is really going to be helpful moving forward. Find the probability that it will be white. So the probability of white or red, or suggests what? Add. Remember we talked about or kind of suggests the word add. So I could find the probability of white and probability of red and add them together. Or you could just combine those at once, actually, in this case. But the probability that it's white would be what? 5 11. 1 over 11 C1. Probability that it's red. 2 11s. It's not changing because you're still just picking 1. So 7 11s. But you could have done that together if you wanted. But here's what's going to be a little bit weird. Suppose you select 2 letters from the word algebra. What is the probability of selecting 2 letters and having the following occur? And it says I shouldn't have to say this. Maybe I will, but no replacement is the situation. So you're not putting the letter back. You pick it, it's used up. Okay, you can't pick that same one again unless it happens to show up twice. All right, so what's the probability of getting 2 consonants in a situation like this? So let's think, consonants. How many consonants do I have? I have 4 consonants, 3 vowels. So if I'm picking 2 consonants from those, 4 C2, there's 4 that I can pick from. Once I pick it, I've used it up. It's a dependent situation, right? So there's 4 to pick from. I'm choosing 2. Now this says, and then how many, it says probability, so how many different ways could I draw 2 cards or 2 letters? Seven C2. I'm reading this to make sure I didn't say anything about the number of unique results, and I didn't. So what about 1 vowel and 1 consonant? What's the probability of getting 1 vowel and 1 consonant? Now notice and, so you're going to be multiplying here. So the probability of getting 1 vowel would be 3C1. Getting 1 consonant would be 4C1 over the total. Again, 7C2. And then 2 vowels would be what? 3C2 over 7C2. Now I'm going to break something down for you and help you to why it's important, and you have to be careful and why sometimes this is going to be more helpful than writing out an alternative. I'm betting that somebody in here is thinking, why can't I go 4/7 times 3/6? Now, 4/7 times 3/6 would say on your first pick, right? I look up there and how many consonants are there to choose from, and there's 4. So there's a 4 in 7 chance that your first pick is a consonant. And you are correct. You can, on your second pick, how many consonants are left? Well, now there's only 3 consonants left. In fact, there's only 6 letters left. So now there's only a 3 in 6 chance on your second consonant. And that is, in this case, the same as this. All right, because this right here happens to be 4 factorial over 2 factorial, 2 factorial. And this happens to be 7 factorial over 5 factorial, 2 factorial. With me on this? And then these 2 factorials cancel, don't they? Because if I were to multiply by a reciprocal, you'd see them cancel. And all I have left is 4 times 3 on the top, because that over that just leaves me a 4 times 3. And then this over this leaves me a 7 times 6. And you can see the 4/7 and the 3/6 right there. But this is why you get into trouble not using these combinations at times. Look at this one. This one is saying right here, right here, let me get rid of this. This is saying 3 factorial over 2 factorial, 1 factorial. This is saying 4 factorial over 3 factorial, 1 factorial. Y'all remember that definition? And on the bottom, it's saying 7 factorial over 5 factorial, 2 factorial. What doesn't happen there that did happen here? The 2's don't cancel. So what that means is, and the 1's really don't mean anything because 1's factorials are just 1's. So what that means is this 2 factorial that's on the bottom of that fraction ends up being on the top of the fraction when you simplify it. Now, you still end up with 3 factorial over 2 factorial, which is 3, and 4 factorial over 3 factorial, which is 4, and 7 factorial over 5 factorial, which is 7/6. But what's that extra 2 factorial, which almost seems like it comes from nowhere? Well, this is where it comes from. If I tell you to pick 1 vowel and 1 consonant, and you say this, 1 vowel, 1 consonant, that's great thinking, except I didn't say what's the probability of picking 1 vowel and then 1 consonant. What you're here is the probability that I'm doing it in that order. But I could also do what? And still achieve this result. 1 consonant and 1 vowel. So there's technically 2 ways to do this. Get a vowel and a consonant, or a consonant and a vowel. If I do this, I have forgotten to count that other way. I could do it in my head and say, oh yeah, there's 2 ways. I could do VC or CV times 2. That's what that does for you. So when you use, it already counts that. You don't have to worry about it. And the beautiful part, it counts it when it needs to count it. And it doesn't matter when you don't need to count it, because when CC, there's only one way to get a consonant. I can't say, oh, I could get a consonant and a consonant, or a consonant and a consonant. That's the same thing. So I didn't need to multiply anything by 2 because there's just one way to go CC. But there's 2 ways to go a vowel and a consonant, VC, and I can count those either like this, or you can count it out front, but sometimes this gets trickier and trickier to count the number of ways to do it. It's almost like counting the number of ways to do that would be at the end, after you do the individual independent probabilities, you basically go back and say something like, how many ways can you arrange the letters in the word Mississippi? 2 factorial. How many ways can you arrange a V and a C? 2 factorial. Mississippi would be like 11 factorial over a bunch of 4 factorials, whatever. That's kind of what I'm doing out front here. If your brain's hurting me saying that, we're going to do that over and over again over the next week and a half. You will get comfortable with it. But you have to remember, if the order in which I do something doesn't have an effect on the outcome, and these orders can be changed, if it's a combination, you've got to account for that. And one easy way is just to use combinations. Now, let me just change this up. What's going to change here if I say there is replacement. If I say there is replacement, can you use combinations? No, you can't, because combinations are built on the idea of a factorial. 4, 3, 2, 1, 7, 6, 5, 4, 3, 2, 1. And if I'm putting it back, I'm not going 4, 3, 2, 1, am I? And I'm not going 7, 6, 5, 4, 3, 2, 1. So if I cannot use combination, so what are the chances of going consonant and then consonant? What are the chances of going consonant, then consonant? Think about them individually. Literally, you're walking up here, pick a consonant. What's the probability that you get one with your eyes closed? 4 and 7? You have to think independently. Now, put the consonant back. What's the probability on your next choice that you get a consonant? But I can't use a combination. Now, vowel and a consonant. Can't use combinations. Cannot. What's the probability that I get a vowel and a consonant? Vowel. 3 and 7? Put it back. Probability of getting a consonant. 4 and 7? But wait, I didn't say a vowel and then a consonant. I just said a vowel and a consonant. You counted one way to do it, right? What else could happen? Consonant, vowel. Now what you're going to do is train yourself not to just literally count them up yourself, because that's going to become much more difficult. You're going to say, well, I'm arranging basically like 2 letters. Think Mississippi. There's 11 letters you're arranging. You would have written 11 factorial if it was Mississippi. If there's 2 letters you're arranging, you're going to do 2 factorial, and there's 1 of each. You're going to learn to say that, okay? What you probably see tonight is you might even see something like, well, there's 7 total letters out there, so the first one doesn't really matter. Sometimes you'll see stuff like, 1, 2, 3, 4, 5, 6, 7. Well, yeah. And then once I pick that, what comes, this would not be my answer, but once I pick that, I've already decided whether it's a vowel and consonant, I pick the other. Well, actually, that would not be a good one. It's not. So you could say a vowel would be, in this case, 3/7, and then 4/6, and then you could just double it. So a lot of times you'll just see it doubled like that on my key. But again, I'm trying to stretch your brain a little bit because it's going to get more and more complicated as we move through this. 18. Throw 2 dice. What's the probability that the same number will show? Now, how many ways can I get the same number to show? 6? 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Right? So there's 6 ways to be successful. How many ways to be unsuccessful? I mean, to be successful or unsuccessful? 36? So you could think that way if you want. You could also say, well, on my first dice, on my first rolls, what do I need to get? Any number. So there's a 6 and 6 chance that I'm successful on my first roll. I still haven't lost, right? But on my second choice, it has to what? Match the first one. And now I only have a 1 and 6, which still ends up being 6 out of 36, right? But can I use a combination or a permutation here? Why not? Because it's an independent situation, right? Rolling a die, I can't use up my 6s, or there's not a lesser chance of getting that once I get it, unless I have a loaded die, but that's not going to happen except maybe on bonus question. I'll let you look at that. And then we're going to jump to this right before the bell rings. Okay, so here's what starts getting interesting. And here's why I really want to point some things out. So this is going to kind of emphasize about once, but you're going to see a little bit more clearly, and maybe see the need for it a little bit more clearly, going back to that vowel consonant question. So this gives you a bag. It's filled up with red, blue, and white marbles. Okay? You're going to pick 3 of them. And the question is, initially, what's the probability of getting 3 red balls? Now, there's a couple ways you can do this. One is using a combination. Because I'm picking, and it's not right. So it's an independent, a dependent situation. I could say, well, how many red balls do I have? 5. So if I have 5 red balls and I choose 3, that's the number of ways to pick 5 red balls, right? Because they are 5, they actually are different, okay? I'm not saying that they're unique. They might all look the same when you pick them, but there are 3 actual, 5C3 ways to do this. How many ways can you pick balls from the container if there's 5, 9, and 6? 20C3? So this is one way to write it. I'm picking 3 red ones from the 3 total marbles. That's one way. And if I do the math on this, I want you to see it. I get 5 factorial over 2 factorial, 3 factorial. I get 20 factorial over 17 factorial, 3 factorial. What happens to the 3 factorials? Cancel. And what do I end up with? What's 5 factorial over 2 factorial? 5, 4, 3, right? And 20 factorial over 17, 20, 19, 18. And if you want to, I'm going to take this 3 factorial right here. When I multiply by a reciprocal, it would have been on the top, right, before it canceled? I could leave those out front. Probably wouldn't do that, but let me just emphasize something to you. This right here is what that is. You can see it. But what I did here is if I think about it independently, it's a dependent situation, but if I think about it one choice at a time, on your first pick, what's the probability that you get a red one? You look up here and you go, well, there's 5 total reds, so there's a 5 in 20 chance that the first one is red. What's the probability that given that you just picked a red one? Well, now there's 1 less red, 1 less total, so there's a 4/19 that the second choice is also red. And then the probability that the third one's red, 3/18. But if all you do is write this, you will be lucky on this problem and unlucky on the next one. And the reason why is, here you are lucky because how many ways are there to go red, red, red? 1. 3 factorial over 3 factorial. Like, how many ways are there to arrange red, red, red? The order doesn't matter, right? 3 factorial over 3 factorial is 1. That's why you would have gotten lucky just writing this. But you'll see in this next problem, I'm going to go red, red, white. Now watch how this changes when I go red, red, white. If I go to red, red, white, look at the difference. Well, first of all, I could do this. If I want the probability of getting 2 reds and a white, I could say 5 reds, I want 2 of them. 6 whites, I want 1 of them. 20 marbles, I want 3 of them. And the combination is already taken care of the different ways I could get a red and a red and a white, whether it's RRW, WRR, whatever, it counts that for me. Check this out, right here. If I simplify this, look at the math. 5 factorial over 3 factorial, 2 factorial. 6 factorial over 5 factorial, 1 factorial. On the bottom, 20 factorial over 17 factorial, 3 factorial. Notice that the 2, 1, 3 don't cancel like the 3 and the 3 did before. What that does for you is when you do the math on this, let's check even more simple. I'm going to write this up top so you can see it cancel better. I'm going to multiply by the reciprocal. Now check it out. What is 5 factorial over 3 factorial? 5, 4. With a 2 factorial left over on the bottom. What's 6 factorial over 5 factorial, 1 factorial? 6. With a 1 factorial left on the bottom, which I know it's equal to 1. What is this over 20 factorial? 20, 19, 18 on the bottom, right? With a 3 factorial left up on the top. What does it look like I just did right here? I found the probability of picking a what? Red. Then the probability of picking another red. Stay with me. Then the probability of picking a what? A Why? Tell me, what is this doing for me? It accounts for the different orders that I could go RRW, just like Mississippi. 3 different letters. I'm arranging all 3, but two are one is another. If you can lock into that, guys, you're going to be in really good shape with this probability. I hope so.